done. It's just, we're really starting to get into the major stuff. So permutation is something very similar to, actually, I should introduce something before I get into permutation, and that's called a factorial. So I need to introduce that first. So factorial is an idea that we've actually already seen. The notation will be some number, so the letter n with an exclamation mark. And this will mean n times n minus 1 times n minus 2 dot 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 all the way down to n minus n. Okay. Whoops. And come on, computer. N minus n. So an example of this, and we touched on this with the multiplication principle. So something like 3 factorial is just 3 times 2 times 1. Okay. So what is that? 3 times 2 is 6. 6 times 1 is 6. So this is the number 6. So that's 3 factorial equals 6. Let's try 4 factorial. 4 factorial is 4 times 3 times 2 times 1. Well, I just figured this one out, 6. So that's 4 times 6, which is 24. Let's do 5 factorial. 5 factorial is just 5 times 4 times 3 times 2 times 1. Well, I just figured out 4 factorial is 24. So I suppose 5 factorial is 5 times 24. And 5 times 2 is 100, and 5 times 4 is 20. So this looks like it's 120. I think that's right. 5 times 24 is 120. Yes. Okay. What about 2 factorial? 2 factorial is just 2 times 1. That's 2. 1 factorial is just 1 times 1. That's 1. And then 0 factorial. This one's kind of weird. So we just have to define it to be the number 1. Okay. Because it's not like we're not going to go into 0 minus 1 times 0 minus 2. We're going to define 0 factorial as equal to 1. We need that with our equations. It had to be something. So we just have to accept that 0 factorial is just 1. That's factorials. It's not it's not super deep. It's just simply an idea. In mathematics, we use it a lot, especially in the higher mathematics. Come on, computer. You guys probably can't see it, but sometimes when I click the whiteboard, it like brings down a menu right under the pen. So that's that's why I keep telling the computer to cooperate with me. Okay, so that's n factorial. It's just a notational thing, but we need it. We need it for the rest of the night, and we'll need it for the rest of the semester, and it's called n factorial. Okay. So we will be using that. Now, the next thing I want to define is called a permutation. Permutation. Okay, and it also gets its own little symbol. We can call it NPR, or you can call it P with N comma R. That's another way of writing it. Permutation is very, very, very similar, if not the exact same thing, of certain multiplication principles that we've already done. It has its own formula, which is n factorial over n minus r factorial. Let's do some examples of that. We've already used permutation in our multiplication principles, but now we're going to kind of expand that idea and solidify it. Let's do some examples. So let's do, say, 3 permutation 2. Let's try that. So as the formula goes, that's 3 factorial divided by 3 minus 2 factorial. Well, what's that going to be? That's 3 factorial. And 3 minus 2 is 1. So that's 1 factorial. So this is 3 times 2 times 1 over just 1 times 1. So that's just 6. And so that just ended up being 6. Okay. Not too bad. Now, I still am claiming that we've done this in multiplication principle, like we did last time. That is 3 times 2 with 2 slots. 2 slots, 3 times 2. This is referring to the slots that we talked about before. And then this is the 3 is the number that we are counting down from. So that's one way to look at it. 5 permutation 3. Let's try this. So by definition, that's 5 factorial over 5 minus 3 factorial. So that's 5 factorial over 5 minus 3 is 2 factorial. So I have 5 times 4 times 3 times 2 times 1 over 2 times 1. And you can see that the 2 times 1 just cancels. So you have 5 times 4 times 3. 5 times 4 is 20, and 20 times 3, I guess, would be 60. So 5 permutation 3 would be 60. Well, in our multiplication principle, this is referring to 3 slots, okay? And then 5 times 4 times 3. And so I claim that that is also 60. So now it's getting its own formula. Now it's, we have a formula for it. If you have a scientific calculator, most scientific calculators have a sequence of buttons that you can press that will calculate it for you. So, for instance, I could have my calculator very easily calculate 24 permutation, I don't know, 12 or something. And I can punch this in my calculator and it will just very quickly calculate that for me. So if you have a scientific calculator, that's something you can do. Just look up how to do permutations on your particular calculator. I would just Google it or type it in YouTube, and you should be able to find some instructions. But that could be another nice thing, is to just check your work using it. Since we're really just we're going to use permutations, everything else is just kind of arithmetic. Okay. Where can this show up in, say, a word problem? Last time we talked a lot about codes. We talked about codes. So let's do an example with that. Let's do a 4-digit code. Okay. No repeats. Meaning, no, we don't want something like 5, 5, 5, 5. We don't want that. Okay. Michelle just ordered a scientific calculator on Amazon. I have a bunch at my disposal. I think I have 5. I own 5 or 6. But we can't meet in person, so my scientific calculators don't really help you. I have, they're on your computer too. I don't know if all scientific calculators on computers have permutations, but it would also depend on what computer system you have. So 4-digit code, no repeats. Let's see what we got. Well, from before, I guess I'll do it in blue, we had 1, 2, 3, 4. And if we have no repeats, we had 10 choices. Remember, we had 0 through 9. So we had 10 choices, 9 choices, 8 choices, 7 choices. I claim that this is the same thing as 10 permutation 4. We have 10 choices, permutation 4, no repeats. That's what permutation means, is the no repetition. So that's another stipulation of when we will use this formula and when we do not. Okay, well, 10 permutation formula, it's equal to 10 times 9 times 8 times 7. Sure, I'm going to also show you on the right-hand side the formula. So that's 10 minus 4 factorial. Okay, that's going to be 10 factorial. And then 10 minus 4 is 6. So that is 10, 9, 8, 7 times 6 factorial over 6 factorial. Cross that out, and you can see that the right-hand side equals the left-hand side. So we should be good to go. What is 10 times 9? Well, that's 90 times 8 is what? 720. 720 times 7 is 540. So I claim it's 540 on both sides of the equation. So that's how we can do it. Now again, there is no repeats. So we can use permutation. So let's do, just going backwards, 4-digit code with repeats. Then I want to use multiplication principle. 1, 2, 3, 4. So I have 0 through 9, 0 through 9, 0 through 9, 0 through 9. There's no repeats, or there is repeats. So 10 times 10 times 10 times 10. I'm not going to use permutation principle. So there's 10, 1, 2, 3, 4. We have 10,000 codes, just like we had Wednesday night, right? We had 10,000 codes out of them. But you can use permutation when you're not dealing with repeats. Okay, so that's something to try to keep in order of when to use. You can always use multiplication principle when talking about permutation. You cannot always use permutation when you're talking about something without repeats. So that's something to keep track of. It's very confusing. That's why we're kind of going over it. Let's do another example. So let's say we're gonna have auditions for a musical. So we're auditioning for a musical, and we have 8 women auditioning, and that's for 4 roles, and we have 5 men auditioning for 3 roles. Okay, so we want to know how many possible casts are there. Okay, so something in this word problem is that we're assuming it's not one of those instances where an actor or actress would play multiple roles. Okay, we're going to do no repeats. Okay, no repeats. Well, there's 8 women and there's 4 roles, so that would be 8 permutation 4. That's how many ways that could happen. And the men would be 5 permutation 3. Now, this is happening at the same time. This is the same instance. It's 2 different things. We have 8 women, 4 roles, 5 men, 3 roles. It's happening in the same instance. So I'm going to multiply. I'm going to multiply these permutations to find the total number of casts. So I hope that's clear what I'm doing. These are 2 events, but they're happening at the same instance. We have 8 women, 4 roles, 5 men, 3 roles. This is happening in the same instance, so I'm going to multiply those permutations. So let's see how this works. So 8 factorial over 8 minus 4 factorial times 5 factorial over 5 minus 2 factorial. So let's see what that would be. That's, well, 8 factorial over 4 factorial times 5 factorial over 3 factorial. And let's see what we get. So I can go 8 times 7 times 6 times 5 times 4 factorial over 4 factorial, and that cancels. So I can get rid of that. That's nice. Times 5 factorial. Oops, I don't want to do that. Let's do 5 times 4 times 3 factorial over 3 factorial. Get rid of that. Now I no longer have a denominator. I no longer have a denominator. So this is going to be 8 times 7 times 6 times 5 times 5 times 4. It's getting pretty big. So 8 times 7 is 56 times 6 is 336 times 5 is 1,680 times 5. 8,400 times 4 is 33,600. I feel like I made a mistake. 8, 7, 6, 5, 5, 4, 3. Yeah, I must have input something wrong. So that's 100,800 casts that could be formed. Okay, that's a lot. That's a lot. Permutations, they get very large very fast. Very large very fast because of this. But that's a pretty good example of a permutation problem. I mean, of course, it's a math problem, so it's kind of silly. Finite, say 5 years ago, or even maybe 7 years ago, there was all these problems about basketball teams and auditioning for roles of plays. And, we'd always tell students, if you see, because IU would always write the exams. And so if you see a play and you're making a play, then you definitely want to use permutation. And if you see a basketball problem, then you always want to do combination. We don't really do those quite as much. So we're going to go through the homework and see what more super modern examples look like. But this is a pretty good example of what a semi-complicated permutation might look like. Now, I will say, if you see something where you're making codes, some kind of code, you're talking a permutation, because it repeats order matters in a big way. And that is a big deal with permutations, is that order matters. So I'm going to write that. Order matters. Okay, what am I talking about? Order matters. I'm saying that the code, say the code 1, 2, 3 is not the same thing as 3, 2, 1. That is not the same thing. And that is not the same thing as 2, 1, 3. Those are not the same. Those are not the same numbers, and order matters. Just like dad is not the same thing as DDA, is not the same thing as ADD. These are not the same things. So order matters with permutation. So that's something we have to keep track of. Okay. Now, hopefully that makes sense. Please ask. Just unmute your microphone if you have any questions. But I want to talk about, what if we have duplicates of something? Now, I just showed the example. Dad is not the same thing as DDA, is not the same thing as ADD. Oops. But there's repeats. There's a repeated D. Okay, there's 2 D's there. So hopefully it's clear, but this is not, the amount of permutations is not 3 permutation 3. 3 permutation 3 is 3 times 2 times 1, and that's 6. There'd be, if that was true, if there's 3 letters here, 1, 2, 3. If we could just use a permutation, then there would be 6 ways to order this, but there isn't because of the repeats. So because of the repeats, we're overcounting. There's only 3 ways to do this. 3 ways. So I need to show you a systematic way of how to account for these repeats, all right? So how do we account for these repeats? Well, it's our divisor, the thing that we are divising by is too small. So we need to take that into account. So what I'm going to show you next is how we account for something that has these repeats, things that are not individualized. So you can do n factorial over r1 factorial, or repeat 1, times repeat 2 factorial, dot, 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 to the kth repeat, okay? So that's like a little formula. If you have repeats, how many permutations you can have. Let's see if I can make this dad work out. So there's 3 letters. So n equals 3, just like before. But how many repeats do I have? I have 2 repeats. So I'll say repeat 1 equals 2. Okay, I have 2 D's. So I say the number of permutations, I only have 1. So this is 3 factorial over 2 factorial, which is just 3 times 2 times 1, 2 times 1. It's just 3. So I claim there's 3 ways to write the letters DAD. DAD, DDA, ADD. Okay, that's the only ways you can write them because of the duplicates. Because of the duplicates. So this is not a permutation. It's kind of a special case because we have the repeats that we have to keep track of this. Hopefully that makes sense. I'm going to show another example though. Another example might be, let's see how many ways I could write the word arrange. Okay, so how many permutations are there with these letters, the word arrange? A-R-R-A-N-G-E. How many ways can we do it? Well, I claim because there's repeats, there's a repeat of the R's, there's repeat of A, and I don't think there's any others. So I claim because of that, we cannot simply just go 1, 2, 3, 4, 5, 6, 7. We can't just say, oh, well, this would be 7 factorial. This would be 7 permutation 7. We can't do that because we have repeats here. So I claim the number of ways to rewrite this is 7 factorial over the amount of repeats. Again, we have 2 A's, we have 2 R's, so this should be good. So 7 factorial, 7 times 6 times 5, 4, 3, 2 factorial, 2 factorial, 2 factorial. I can get rid of 1. That's nice. 2 factorial is just 2. It's 2 times 1. So I can also reduce out this. I can reduce out the number 2. I could reduce the number 4. 4 divided by 2 is just 2. So now I have 7 times 6 times 5 times 2. You could have just as well reduced the 6 to a 3 if you want. I just picked the next one. Oh, and don't forget that 3 over there. So this should be our answer. This should be the number of ways that that's possible. 7 times 6, 42, times 5 is 210, times 2 is 420, times 3 is 1,260. So I claim that would be the amount of ways that you could rearrange the word arrange. I would not want to count those out. I wouldn't want to count 1,260 different ways. I don't mind counting 3-letter words. That's okay. I could do that all day, but I don't want to count the number of ways for a range. Okay. Just to make sure we got it, let's try another one. Just want to make absolute sure. Can you see this green? Is that visible for you, or is it too faint?
I can see it.
Okay, good. Okay, how about the word rearrange? Let's see if we could figure out how many permutations. This is an even longer word. So how many permutations can we do for this one? 1, 2, 3, 4, 5, 6, 7, 8, 9. There's 9 letters. Okay. So I claim that that would be 9 factorial. And then how many repeats do we have? Well, I have a repeat with R. This is a repeat, repeat, repeat. So it looks like I have 3 R's. Okay. What about E's? I think I have a repeat of an E here and here. So that's 2 factorial. And then what about A's? Yeah, I have 2 A's. And I don't have a repeat of N. And I don't have a repeat of G. So I think I'm done as far as setting up the formula goes. Let's see what I think this formula would be. Let's do the arithmetic. So 9 factorial is 9 times 8 times 7 times 6 times 5 times 4 times 3 factorial. I always like to stop at the biggest one in the denominator. 3 factorial, 2 factorial, 2 factorial. Cross that 3 off. There we go. Okay. Well, I have 2 factorial is just 2. 2 factorial is just 2. 2 times 2 is 4. So if you'll let me, I'm going to reduce these 2 times 2, just get rid of that 4 altogether. So I think the answer is just 9 times 8 times 7 times 6 times 5. Okay, let's see what that is. 9 times 8, 70, 72. No, 9 times 8, 72 times 7 times 6 times 5. Very large number. 15,120 different ways to rearrange the word rearrange. Okay, so that's quite a bit. You would not want to count those by hand. That's for sure. But we can easily program a computer to do it for us, to rearrange all these slots, to rearrange different members of the corporation, to rearrange anything. And we can even program without having these duplicates, or without having, with that in mind, we can easily do that. Ivy Tech, many colleges arrange students by their student ID number. And so we could imagine that we could do a lot of manipulation with just identifying a student with a number or a sequence of numbers and letters. You can imagine you could do quite a bit just with these simple ideas, and figure out how to rearrange things. So that should hopefully spark your imagination of how you could work with that. Let's do, I think we should do at least one more example before we look at the homework and make sure everything makes sense. So let's talk about this next one. Let's talk about lunch specials. Kind of silly. But certainly we all had lunch specials in high school, for sure. Let's look over the next 10 days. Okay. And we're going to have 6 days be burritos. That's a lot of burritos. A lot of repeats. 6 burritos 6 times. And we're going to have clam chowder for 3 days. 3 times. And spaghetti just once. It wouldn't be plural. It's just one time. So how many different ways can we do this? How many ways? How many ways? Well, we certainly have some repeats. That's for sure. We have 10 days. We have 6 burrito days. So that's repeat. And we have 3 clam chowder. Okay. And if you want, you can even put the spaghetti, which is just 1. You can put 1 factorial. That won't, even though it's not technically a repeat, if you prefer that. Some students do. Just so we've counted everything, you can put 1 time for that. So this, I claim, will be how many different ways this meal plan could work. How many different ways? So 10 times 9 times 8 times 7 times 6 factorial over 6 factorial. I can cancel that off. 3 factorial is 3 times 2 times 1, which is also 6, and then times 1. Okay, so let's see. We have a 3 here, and I have a 9 here, so I can turn that 9 into a 3. I have a 2. I have an 8, so I could turn that 8 into a 4. That'd make it a little bit easier. So 10 times 3 times 4 times 7. Well, that's going to be 30 times 4, which is 120, times 7, which would be 700, plus 140, that's 840. Okay, so I claim that there's 840 ways to have this meal plan with those restrictions. You could also imagine that might be if you had to plan for a major amount of people, that this would be a way to do that. So I think that is, I mean, it's not a super deep lesson, but it has a lot of implications, and it's really, really important for our class. And it's actually a really important idea. So I think now, unless there's any questions, we can just start looking at the homework. Okay, so I'll stop sharing that. If you'll give me 1